Thank you very much, Professor. Good morning, everyone, and welcome to my presentation. I hope everyone can see the screen now and hear me clearly.
Yes, go ahead.
Okay, perfect. So I will use the next 15 minutes to introduce our new model order reduction method based on singular perturbation. But first, let me start off by explaining the background and motivation of this work. Dynamic power system simulations are an integral part of power system research and design and have been around ever since computational power and the costs thereof have made it a viable option. In recent years, however, multiple factors have contributed to making large-scale dynamic power system simulations computationally challenging. Let me go into detail with a couple of those examples. Firstly, the spread of decentralized inverter-based generation. This forces simulations to include more and more individual units. The increase can be seen in the plot on the left-hand side, which shows the large growth rate for solar and wind power. This increase has two effects on simulation complexity. Firstly, the number of units that are individually modeled, and secondly, the complexity of inverter models themselves. This is because inverter models used in dynamic power system simulations consist of more states than models of synchronous generators. An example for that is shown in the inverter control scheme, which is on your screen now. This is a commonly used model in power system simulations, and we've already seen it in one of the previous presentations, or a close adaptation to it. Let's take a quick look at the model. On the right-hand side, we can see the electrical system. It consists of 3 measurements, 2 current and 1 voltage measurement. Since the model is in DQ frame, every measurement is described by 2 states, one for the D and another for the Q component. On the left-hand side, we can see the controls of the inverter, which are split up into a system level and device level control. System level control contains an active and a reactive power controller, which are the orange and red blocks respectively, and also the phase lock loop, which is shown in the green block. The phase lock loop enables the model to be used in grid following mode, where it synchronizes the outputs of the controllers to the voltage conditions at the point of connection. The last point I would like to mention, which contributes to an increase in computational effort, is tied to the timescale of inverter dynamics. So let's compare the blue blocks, which are the components of a synchronous generator model, to the red blocks, which are the components of an inverter model. Not only do the dynamics of inverters act on smaller timescales, the blocks here are further to the left, but they're also spread across multiple timescales. This has a direct impact on solver time during dynamic simulations. A possible way of counteracting the increased computational burden caused by the factors just mentioned is to reduce the model order. This comes with a trade-off, however, in the name of model accuracy, which is especially important for predicting current peaks during dynamic behavior in order to protect inverter circuits. A commonly used model order reduction method in power system engineering is singular perturbation. We have decided to base our reduction efforts on this method to take advantage of the different timescales in the model. In order to understand our contributions, let me begin with a brief mathematical overview of singular perturbation, starting with this system of first-order ordinary differential equations. Traditional singular perturbation theory focuses on timescale differences within the model, which is to be reduced. The differential equations are reformulated such that the left-hand side consists of a differential term multiplied by a timescale defining parameter. These parameters are here shown as a diagonal matrix epsilon, 1 factor per equation. The system is then split up into slow and fast states and equations depending on the magnitude of epsilon. Equations with a large parameter are defined as slow, here with subscript s, and equations with small parameters are defined as fast, subscript f. In the next step, it is assumed that the fast equations reach a quasi-steady state immediately. Therefore, the equations are set to 0. The newly formed algebraic equations now act as constraints for the differential equations of the slow states that remain. The resulting model is now of lower order, which, however, comes at the cost of model accuracy. From here on out, I will call this method the zero-order singular perturbation. In recent literature, an adaptation of this method has been proposed. This new method was introduced as first-order singular perturbation by the authors and is only applicable to linear models. Since the inverter model at hand, which I've briefly introduced you to, is nonlinear, we derive the same method but for nonlinear models. Let's take a look at the math behind it. Similarly to than before, this method takes advantage of the split up into slow and fast states. In contrast, though, to singular, before the fast equations are taking derivative, and this new is set to 0. After some reformulation, the result is a reduced order model with algebraic constraints. This time, however, the constraints, let me move ahead here, contain more of the dynamic information of the fast states than in the zero-order singular perturbation, which we see on the left-hand side. Before I continue explaining the contributions of this work, I would like to quickly recap the key differences of zero and first-order singular perturbation. Zero order, or the traditional singular perturbation method, is commonly used in power system model and uses small parameters to separate the system into slow and fast states. The dynamics of the fast states are neglected in order to improve computational performance. It is therefore only possible to distinguish between two different timescales. Most of the points also apply to the first order method. However, the complex algebraic constraints allow for a more accurate reduced order model at the cost of computational effort. In the process of finding an adequate reduction method for the introduced inverter model, we decided to combine the two methods in order to take advantage of both upsides, and we call it hybrid singular perturbation. Let me show you what I mean by that. Since in hybrid singular perturbation, we plan on using zero and first order reduction at the same time, the system can be split into 3 timescales. Before we had only slow and fast, now we have slow, fast, and very fast states, which are here represented by subscript V. The equations of the slow states remain untouched. The equations of the fast states are reduced using the first order singular perturbation method, and the equations of the very fast states are reduced using zero order singular perturbation. Or in other words, the faster the dynamics, the less information will be retained in the reduced order model. As introduced before, this means taking the derivative of the fast equations and setting the new expression equal to 0. And also, this means setting the equations of the very fast states to 0. This is just the methods shown before applied both on the same model. The result is a reduced order model with 2 sets of algebraic constraints, one coming from the first order approach, one from the zero order approach, and they both have different complexities. Okay, to sum it up, the hybrid method allows for the separation into 3 timescales, not only 2, namely slow, fast, and very fast. This allows for the reduction of different timescales with the appropriate reduction method, therefore combining the computational efficiency of zero-order singular perturbation with the model accuracy of first-order singular perturbation. As you may have noted, the small parameters used in traditional singular perturbation were not present in the derivations of the first and hybrid method. This is because we chose to use participation factors instead of small parameters to determine the time scales of the states. By computing the eigenfrequencies, which you can see in the second column of all the modes, and then mapping the influence of states on modes using participation factors, which is the middle column, we were able to separate the states into 3 timescales, the results of which are seen in the table. Clearly, the electrical states, which participate the most in the modes with the highest eigenfrequencies, so the ones above 500 radian per second, are the very fast states of the model. Therefore, the electrical states, VF, IG, and IF, the top 3 in the list, are the very fast states. After that, the states Xi and theta S, which is the PLL state, are good candidates for fast states, while the rest of the states are considered as slow. To evaluate the performance of our method and to compare it to the traditional method, we ran simulations using a grid following inverter model, the one I showed before. In order to force dynamic behavior, a fault scenario was introduced. The fault is caused by instant opening of K1 and K2 as seen in the single line diagram below. This resembles a disconnection of one of two parallel connectors. Also, we introduced two metrics to quantify the results. Firstly, simulation runtime, which was averaged over 100 runs. And secondly, model accuracy, which is captured by the root mean square error of the time domain response of the reduced order model. This has all been done with the full order model as a benchmark. So let's have a look at the effect of the fault on the time domain response of the active power output of the inverter. This plot shows the response of the full order model, which consists of 15 differential states. As we saw in the table before, the fastest 8 states are categorized as very fast and therefore reduced using zero order singular perturbation. To observe the effects of model reduction, we start by removing the fastest states, 2 states at a time, because of the D and Q component, starting with the electrical states. Model orders 13 and 11, which is the blue response shown, show almost no loss in model accuracy. The fast oscillations of the response, however, are lost when reducing further, no, I moved ahead too quickly, to model orders 9 and 7, which is the red response. However, the overall error compared to the full order model is still very small and the overshoot is captured fairly well. This changes when using zero order singular perturbation to reach model orders 6 and 5. Suddenly a large error is introduced, indicating that the last state reduced, going from order 7 to 6, contained valuable dynamic information. This state, theta S, again the PLL state, was previously declared as fast and not very fast, and therefore should be reduced using first order singular perturbation. This last domain plot that I will be showing you compares the fifth order model in two different versions. First of all, the full line, which is the response we just saw in the plot before for model order 5 and 6, and the dashed line, which is the response for the model after having applied hybrid singular perturbation opposed to zero order singular perturbation, meaning that going from order 7 to 6, first order singular perturbation was applied. It is seen that the hybrid approach is more accurate in two ways. Firstly, in the quickness of the response, and secondly, in the approximation of the positive overshoot. Well, let's see if we can capture this quantitatively with the benchmarks we introduced. Starting with the plot at the top right, the runtime of the reduced order model using zero order singular perturbation, again depicted by the full line, is compared to the runtime of the output of the hybrid method, the dashed line. The model orders are shown on the x-axis and the runtime on the y-axis. For model orders 15 through 7, almost no difference is seen. Actually, no difference is seen at all, as all of the states were reduced using zero order singular perturbation because the states were determined to be very fast. For model orders 6 and 5, the hybrid method results in a reduced order model with a slightly longer runtime, which can be seen as the dashed line is higher than the full line. This was also the expected behavior, since the reduced order model is more complex when we introduce the hybrid method. However, this increase in runtime is compensated by a higher model response accuracy, which is seen in the two plots below. The plot with the red line compares the root mean square error of the active power response between the two methods. The plot with the yellow line shows the response of the voltage at the inverter connection point. Especially the improvement for the active power output is remarkable and contributes to overcurrent protection of inverter circuits. And with that, I would like to sum up the key findings of our work. We introduced a novel reduction method based on singular perturbation. This method is applicable to nonlinear systems, and it combines the advantages of zero and first order singular perturbation. This method is especially useful when more than two distinct timescales are present in the model and can then be taken advantage of. Also, the performance of the introduced method was analyzed in a small case study, as I just showed you, where runtime and time domain response accuracy were compared. The slightly longer runtimes of the hybrid method were compensated by the improved reduced order model accuracy, especially for the active power output, which has the largest influence on the inverter current. And finally, a small outlook. Further evaluations could involve the application of this method to an IEEE test system, including multiple VSCs and synchronous generators. And it would also be interesting to reduce the system, including line dynamics, since some interesting timescales will be introduced, which this method could be taken advantage of. And with that, I would like to thank everybody for their attention, and I'm looking forward to your questions.
Thank you very much, Ivo, for the concise presentation. So we have already four questions plus one coming from one of our panelists. So let's start with the one of Joachim Björk. So does the first order singular perturbation preserving the physical meaning of the variables? Have you compared the results to balanced model reduction?
No, we have not done that. Prior to the work, I did a broad scan of different reduction methods, and I also came across balanced reduction method, but we did not do a comparison.
And about the first part of the question, so he's asking whether the...
Can I see the question somewhere? Sorry.
Is preserving the physical meaning of the variables.
Yes, absolutely. Yes, this method preserves the physical meaning of the variables, which is one of the reasons why we chose this method, because therefore we could still understand the output fairly well.
Okay.
So the reduced order model, yes, exactly.
Excellent. So second question from Professor Cherkaoui. So as I asked it to Taufik in the first presentation, did you perform any simulation with this model included in case of multi-sources systems, including, for instance, several synchronous machines?
No, we have not done that performance, although this is one point of interest that we would like to perform in next couple of months.
Okay. So there was then in the queue a question from Taufik. So Taufik, can you unmute and ask your question, please?
Okay, thank you. So before asking the question, could you please confirm that you said that you are using grid following control? Did you confirm that you are keeping the voltage regulation loop first?
Yes, exactly.
Okay,
so you want me to go back to the model quickly?
Okay.
It's quite a way here.
Okay.
Exactly.
Okay, great. So the order model reduction that you are using, it assumes a good decoupling between all these control loops, which is not an easy task. So how could you know that all your that you don't have any parameters that create interactions between eigenvalues, and how could you solve that with your method?
So the eigenvalues only came into part when using the participation factors, right? Where we determine which are the fast states and the slow states. And let me go back to the table. I hope I understood your question correctly. As you can see, the participation factors they usually only show the majority of the participation of a variable to an eigenvalue or a mode itself. All the other participation is kind of lost in this analysis, right? All the other influences of the variables on the same mode.
I mean, if you have another tuning of controllers, you will not have the same decoupling between state variables. So how could you solve that in case of interactions between controllers?
A different parameterization of the inverter model.
Yes, right.
Actually, I tried a bunch of parameterizations, but all fairly similar, and we always got the same result or similar result to the table that I'm showing you here. So I have no experience with effects of parameterization on coupling there.
Okay. Yeah. Thank you.
Excellent. So I guess we have time for another question, although there are 4 questions in the queue. So the next one is from Zhao Yuan. So he's asking essentially, which are the criteria to separate the system in slow, fast, and very fast subsystems. He's asking which is the concept, the standard concept to adopt in this separation, and whether it is based on the parameter WK that you showed in slide 8 and 9.
Yes, it is definitely based on the parameter WK, but there's no hard rule how to do it, right? So the method that we applied, and since we've never done this before, we had some trial and error as well, is you can see that the eigenfrequencies of the first 6 states, because we have complex states, are far larger than the eigenfrequencies of all the other ones. So we can kind of say we want to eliminate these modes and therefore want to find the state variables with the largest participation in those modes. After that, it's not as clear anymore how to divide up these middle states, whether to call them fast or very fast or slow even. Yeah, we came up with reducing the first 8 states using defining them as very fast. The next one, the PLL angle, as fast state, and the rest as slow states. So no hard rule, but some experience showed that this was the best approach.